So the topic we'll be discussing in this lecture is logical agents. So we'll be moving to the next chapter now. So this is chapter number 7 as per the textbook. So with what we have discussed in the last lecture, with that we'll be stop discussing adversarial search. So what is the core thing here we are going to discuss? As the name suggests, it is logical agents. That is, agent is going to apply some logics. So before that, what is a logic? See, logic is a basic method of representation of facts. Logic is a basic method of representation of facts. And from these facts, further facts can be derived. So that is what the role of logic. And the concept of logic is very old. It is a pretty old concept. It exists since the time of Aristotle. So Aristotle has first derived the idea of logics, right? So this is something like a quotation which gives an abstract idea about what we are going to discuss. So the topic we are going to discuss is logical agents, in which we design agents. We design agents such that these agents can form representation of a complex world. That is, these agents will be having the capability to represent the complex world, and also it will use some inference mechanism to derive new representation of the world. And using this new representation, they can deduce or they can further infer like what they are supposed to do, right? So that is what we are going to discuss in this lecture. That is, the logical agents can represent, they have some mechanism to represent the complex world. And apart from that, they can also apply some inference mechanism, and they can come with some new representations, that is some new knowledge. And from this new knowledge, they can decide like what they are supposed to do. Fine. So to start with, see humans are the intelligent beings which we know. So humans know things. So if you take a typical human being, they know certain things. And so this knowing the things means something like a knowledge. So this knowledge is represented in the human. Where it is represented? It is represented in the brain or mind or whatever it may be. That is philosophical aspect. Let us not go and get into that. But somehow, somewhere in the human, the knowledge is represented. So based on that only they know things. And this knowledge helps them to do things. And based on this knowledge only, they are doing things. So they are confident enough to do certain things. So this is not an empty statement. This is a real truth. This is how the human beings work. Okay. And humans do not work just by reflex mechanism. So it's not just a reflex mechanism. It's not a reactive mechanism in which a human work. Rather, by reasoning, they reason. They learn over a period of time. They analyze the facts and then they make decision. Okay. So if you are able to make an AI system to do that, then such systems are called as knowledge-based systems. So in an artificial intelligence system, if we could provide the ability to represent knowledge, and if that system can learn over a period of time, that is, if it can infer, so not exactly learning, if it can infer, if it can deduce new facts, if it can infer new facts from the existing facts, and based on the new facts, if it could make some decisions, then such systems are called as knowledge-based systems. So we have discussed several ways of problem solving in chapter 3 and 4. Like we have discussed heuristic search. Before that, we have discussed uninformed search, informed search, all those things. But they know things in a limited way. So they are strictly based on that algorithm. The algorithm only controls the things, right? So for example, the problem solving agents, which we have discussed in the previous classes, like uninformed search or informed search or heuristic search, whatever you see, they are generally they are inflexible. They are not flexible. So they normally try to explore every possible states. Of course, we generally they explore every possible states. We tried some refinement, like for example, if you take the minimax search, it tries to explore every states, right? Then we have reduced some improvement over that by using alpha beta pruning, but the basic version actually tries to explore every possible state. So this is applicable to almost all the algorithms. So such algorithms or such problem solving agents were generally seems to be inflexible, and in most cases their search complexity is exponential in time. And further, these problem solving agents, they cannot infer unobserved information. So based on some existing info, they cannot infer new things. They cannot infer new knowledge, right? So because of these things, we say that because of these things, we are moving to the next level of artificial intelligence, or the next level of agents, which is called as logical agents, right? So if an agent is using logics, that is, if it is has the ability to represent knowledge, and if it can infer new facts from the existing knowledge, then such a system is called as knowledge based system. Then such a system is called as a knowledge based system. And the central component of a knowledge based system is a knowledge base. So knowledge base is something like a database which contains set of sentences. So knowledge base is not something like a database which contains set of sentences. So these sentences are also called as facts. But these facts can take either the value of true or false. Okay, sometimes it may take the value true, or sometimes it may take the value false, depending on the situation. And the sentences, how we will represent the sentence? These sentences are represented by using some languages. So these languages are called as knowledge representation language. Okay. So actually there are many such languages. So as we have already mentioned, this logic is a concept which is a very old concept. It is existing since the time of Aristotle. So since the time of Aristotle itself, there are many ways to represent the knowledge. For example, one of the common way to represent knowledge is called as propositional logic. Propositional logic is one of the simplest way to represent knowledge. We can only represent set of facts, and these facts can take truth value. Either it can be true or false. The another form of logic is something called as predicate logic. Predicate logic is also called as first order logic, right? Similarly, there are different types of logics are available. Say there is something called as probabilistic logic. These are little advanced, so they also include some kind of probability. And we have fuzzy logic. So like that, there are all these are nothing but different knowledge representation languages. Propositional logic is one way of representing knowledge. Predicate logic is another way of representing logic. Probabilistic logic is another way of representing logic. Fuzzy logic is another way of representing logic. Okay, so they all have their own vocabulary. They all have their own syntaxes. So for example, if you take any language, there is a syntax. Right? Even if you take it need not be a programming language. Even if you take a language like English or Hindi or Telugu, there is some syntax, right? So the syntax represents the rules or the grammar of the language, right? So similarly, for these languages also there are some syntaxes, and also, so when syntax is there, obviously there will be also some semantics. So syntax represents the way of representation, and semantics represents the actually what they mean. Okay. Right. See, some of these sentences are also called as axioms. Axiom is basically, it is a sentence. It is a sentence uh, but a sentence which cannot be derived, such sentence are called as axioms. So these are not derived from any other sentence. These are something like very basic facts which cannot be proved. So for example, there is a very basic fact which is generally acceptable by all. So assume there is a basic fact which is generally acceptable by all, and there is no way to prove that. Okay, generally accepted by all, and there is no way to prove that, and you cannot prove it. Such sentences should be represented in the system, and they are called as axioms. Right? So there is no formal way to prove that, but it is a known fact. So such sentences are called as axioms. So these are some of the terms which you will encounter, and sometimes we may want to add new sentences to the knowledge base. So you can add a new sentence to a knowledge base by using a command called as tell. So tell is a method to add new sentences to the knowledge base. Similarly, if you want to query the knowledge base, the method is to use ask. So ask is something like a command which is used to query the knowledge base. Now you can ask the knowledge base. The knowledge base, based on its sentences, it will give some answer for whatever you ask. Right? And inference. What is inference? Inference is deriving new sentence from the old sentences is called as inference. So it means we are deriving so it means the knowledge base, the agent. So basically, agent is using the knowledge base. So the agent is using the knowledge base, and the knowledge base contains many old sentences. From the old sentence, if the agent derives new sentences, then that is called as inferences. Right? Again, tell and ask also may involve inference. What does it mean? Tell means, say for example, the knowledge base already it contains some sentences, right? Now assume that the user is giving a new sentence. User is adding a new sentence to the knowledge base through tell. So user is feeling this is a basic fact, maybe something like axiom. So user is adding this sentence to the knowledge base. Now the knowledge base has got an additionally one sentence. Previously, say if it has n sentences, now it has n plus one sentence. Now once this new sentence was added, the agent may, based on this new sentence, the agent may infer some new things. And it may add some further new sentences the agent can add. So tell can create inference, right? Similarly, ask may also create inference. Say for example, the user is asking the knowledge base some question, whether what is some question he is asking. So based on this, say there is no direct answer available in the knowledge base. Whatever the question the user has asked, there is no direct answer available here. Now the knowledge base will analyze all the sentences whatever available, and based on this sentence, it will make some inference and it will give a reply. So now as a result of this, it has created a new sentence. So that new sentence also it will add. Okay. So see, this logics we are talking about basic logics. So I'm not talking about fuzzy logic or anything like that. So these basic logics they are very perfect. So for example, that means there is no ambiguity in them. There will not be any ambiguity. So for example, so this is a very standard example. Say these are some of the basic axioms you are adding to the knowledge base. Say like all men are mortal. All men are mortal. This is a sentence you are adding, okay, and you are saying that Socrates is a man. Say these are already added to the data, to the knowledge base. Now say for example, you are asking the knowledge base like, is Socrates is mortal? Is Socrates is mortal? You are asking a question, is he is mortal or not? Now there is no direct info available here whether Socrates is a mortal or not. Only there is available Socrates is a man, and there is something all men are mortal. Now the agent can infer The agent, with this fact, the agent can infer that Socrates is mortal. So it is 100% truth. There is no doubt in that. So there is no ambiguity in that. So because from these two facts, the agent can derive a new fact which is called Socrates is mortal. So this new fact will be added here. Socrates is mortal. Are you getting? And also the agent will reply to the user that yes, Socrates is mortal. Something like that. So uh, so what I'm trying to say in the sense, in case of very fundamental, when you apply the fundamental logic like propositional logic, there is no ambiguity. They will create strictly logical sentences. That is, they will create strictly the sentence that will be either true or correct. There is no confusion like whether it is true or not. No, nothing like that. Okay. Fine. So that is about tell and ask. So basically, we to address the issues that are connected with the problem solving agent, we are going for knowledge based agent. So knowledge based agent includes knowledge base, and also it contains rules for inferences, and also it provides uh, logic which is used to process the statements, or the knowledge base contains statements. The statements will be effectively processed. The logic provides the mechanism to represent the statement, and also it provides mechanism to infer new facts from the existing facts, right? Okay. So knowledge base, so if you see knowledge base is basically domain specific content, right? Say so domain specific means it is related to a particular domain. So when you talk about chess, the knowledge base will be specific to chess game, the rules of the chess game. It will be limited to that. But when you see the inference engine, so inference engine is something at the top of the knowledge base. So knowledge base is something like a database which contains set of statements, but these set of statements are specific to a particular domain. But this inference engine is very generic. It is domain independent. These are domain independent algorithms. That is, these algorithms can be applied on knowledge base of any domain, right? Okay. And the agent which will be the agent is the one which is going to use the knowledge base and make the inference, all those things. And the agent can be viewed either at the knowledge level, or it can be viewed at the implementation. Knowledge level means it is something like a high level abstraction. It is like a high level of abstraction. That is the agent know what they know, but the agent does not know how it is implemented. So it is like a top level understanding. So if the agent is viewed at knowledge level, so this is if the agent is viewed at knowledge level, it is a high level of abstraction. That is now the agent know like what it knows, what are the things it knows that the agent knows, but agent actually don't know how it is implemented. Right? But if you see the agent at the implementation level, if you view the agent at the implementation level, then it also knows like how the whatever it knows, how it knows also it knows. So what data structure is used in knowledge base, and what are the algorithms that manipulate them, everything it knows. If it is if you are viewing the knowledge, if you are viewing the agent at implementation level. Okay. Fine. Okay, so this is the introduction to the logical agents. Now let us let us understand the logical agents with an example. So we'll be discussing an example. This example is called as Wumpus world example. First, this problem we are representing this problem in PEAS description, which we have learned previously. P stands for performance measure, E stands for environment, A stands for actuators, and S stands for sensors. Right. So what is the problem? This is the problem. Say this is like there are different rooms. So there are 16 rooms are here. So this is something like a den. So this is something like a den. This den contains 16 different rooms, and the agent is starting here. Assume you are the agent. The agent is starting here, and this den contains some of the rooms. Actually, they contain pit. Some of the rooms contain pits. if the agent enters this room, the agent will die by falling into the pit. Okay, so it means the agent should not enter into the room, but the agent don't know which room contains pit, right? By accidentally, if the agent enters the room which contains pit, then the agent will die. And one of the room contains what you call a devil-like creature called Wumpus. One of the room contains a devil-like creature called Wumpus. And this Wumpus will be only in this room. The Wumpus will not change its room. Okay, Wumpus will not change its room. And agent should not enter this room also. By accidentally, if the agent enters this room, Wumpus will kill the agent. Okay, but agent is given with one arrow. Agent is having one arrow. If the agent faces the Wumpus face to face, if the agent meets the Wumpus face to face inside the room, and if he fires that arrow, then Wumpus will die. So there is that possibility also. Okay, so it's not that always if the agent enters the room of the Wumpus, the agent will die. No. For example, if the agent is meeting the Wumpus face to face, and if he fires or if he shoots, if he is having the arrow and if he shoots, then the Wumpus will die. But the agent has only one arrow. Okay, so this is the second condition, and there are, we have certain hints. The rooms that are adjacent to the pit, there will be breeze in that rooms. Whichever the rooms that are adjacent to pit, there will be breeze. So adjacent in the sense they should be adjacent. What you call they should be adjacent in the straight way, not diagonally. Okay, so for example, here there is a pit. So there is a breeze in this room, there is a breeze in this room, and also there is a breeze in this room, right? Here there is a pit, there is a breeze in this room, there is a breeze in this room, there is breeze in this room, right? So wherever there is a pit in the adjacent rooms, there will be breeze. And wherever there is Wumpus in the adjacent room, there will be stench. There will be some bad smell. So Wumpus is here. So in this room, there is a bad smell. Here also there is a bad smell. And here also there is a bad smell. Right? And one of the room contains gold. One of the room contains gold. So actually the agent is here to get the gold. The agent is here to get the gold. Right? So this is the problem statement. Okay. So now we are trying to solve this problem by using logic. Fine. Okay. So the performance measure is what? If the agent gets gold, then the agent will get 1000 points extra. If the agent dies, then he will be decreased by 1000 points. His score will decrease by 1000. And whenever agent makes one step, his score will be decreased by 1. And if the agent uses the arrow, his score will be decreased by 10, minus 10. And this is the environment specification. Squares adjacent to Wumpus or smelly, that is the stench. Squares adjacent to pit or breezy. And glitter if gold is in the same square. So if the agent enters this square, how do the agent knows that there is a gold? So there will be a glitter, but only within this room. So whenever there is if this room contains gold, then the glitter will be only within this. So if the agent enters the room and there is a glitter, then the agent will understand that there is a gold, right? Glitter if and only if gold is in the same square. Shooting kills Wumpus if you are facing it. So shooting will kill the Wumpus if the agent is facing the Wumpus. Shooting uses up the only arrow, right? And there is an action the agent can do for grabbing the gold. So grabbing is an action which is used to pick up the gold if the gold is in the same square. And releasing is also an action the agent can do, which is used to drop the gold, right? And these are so we let us assume that the agent has the capability, the agent has sensors to sense these things. The agent can sense the stench smell. The agent can sense the stench or the smell, the bad smell. The agent can sense the breeze. The agent can sense the glitter and bump. What is bump? So it is not that all flow, what you call, see, this is a wall. This is a, so agent is currently in this room, but there is a wall between these two rooms. So if the agent want to go from this room to this room, it is possible only if there is a door. Similarly, the agent can go from this room to this room only if there is a door. So it is not that there is a door available between every two rooms. Between some rooms, the door may not be available, right? In that case, the agent will experience a bump. It means he is hitting on the wall. So it means he cannot go in that direction. For example, the simple example here you can understand is the agent is here. He cannot go this side. There is nothing here. So he cannot go move to the left. So if he tries to move to the left, he will experience bump, right? And scream. So if Wumpus dies, then it will make a big sound. So that is called a scream. So if Wumpus dies, no, then it will make a big sound. That sound will be visible in all the rooms, right? So suppose agent may be here. Agent may be here only, but suppose the agent, say for example, the agent hears the scream sound, then the agent can assume that the Wumpus has died. Okay, so that's the concept. Fine. So these are the sensors, and these are the actuators. What the agent can do: agent can turn left, the agent can turn right, the agent can move forward, the agent can grab, release, and shoot. Okay. So turn left means he is changing the direction. For example, currently agent is facing this direction, but if he want to go to this room, then you have to change it. Turn right. First turn right, then you can move forward to go to this particular room. Okay. So that's the reason why this left turn, right turn, all these are given. So this is the problem definition. Now, if you consider this problem, is it fully observable? It's not fully observable because agent knows only very limited information about that particular square, and also probably if there is a breeze or stench, then he can have some little information about the adjacent square, but not fully. So it's not a fully observable environment. Is it deterministic? Yes, that is what the agent will do next. That is deterministic. For example, currently the agent is here. Okay, so here the agent is not sensing anything. There is no breeze. There is no stench. It means the agent knows that if I move here, I will reach to square 2. That he knows. So it is deterministic in the context what? If he moves right, he will reach the square. So this is square 2 comma, this is square 1 comma 1 means this is 2 comma 1. If he moves right, he will go to square 2 comma 1, that he knows. If he moves up, he will go to square 1 comma 2. Okay, so all these things the agent knows. So in that context, we are saying that it is what you call, it is deterministic. Is it episodic? It's not episodic because the previous decision will also have an impact on the future decision. Is it static? Yes, it is static because the Wumpus or the pit, or they are not going to change its position. So it is static. Is it discrete? Yes, it's discrete. It's not dynamic. It's not continuous. When the agent makes a move, only the next state will change. So it is nobody else is going to change the state. Is it single agent? Yes, there is only one agent. Wumpus is not considered as an agent here, right? Because Wumpus is not going to make any move. So this is the problem characterization. Now let us see how we will solve this. So first, we are not using any logics, but from a human point of view, how we will solve. Then we will connect with logic. So currently, if you see, agent is in this square. So is there any problem in this square? No, there is no problem. So you can say it is okay square. So it's okay. It's okay in the sense there is here the agent is not sensing anything. No breeze, no stench, which means that the agent can comfortably move here or he can move here. Both places are safe for the agent. There is no doubt. So the agent is here. This is okay. So it means agent can go here. This is also okay and this is also okay. Right? Okay. Let us assume that the agent is moving here. Now the agent has moved here. When the agent moves here, what he will sense? So here there is a breeze. Here there is breeze. So when the agent moves here, he experiences breeze. He experiences breeze. But when breeze is there, what does it mean? the adjacent square has a pit. Now which square? Whether is it this square or this square or this square? There are three possibilities. But agent has come from this square. Okay, agent has came from this square. So agent knows that there is no pit here. Agent knows that there is no pit in 1, 1. So this is 1, 1, right? So agent knows that there is no pit in 1, 1. So probably there can be a pit in, this is 2, 1. This is 3, 1, right? This is x-axis 3, y-axis, yeah. So probably there can be a pit in 3, 1. So this is 1, 2, 3, 4. Again, this is 1, 2, 3, 4. Okay. So this is, so probably there may be a pit in 3, 1, or there may be a pit in 2, 2. Right. So now what the agent will do? Now the agent cannot take the risk. If he goes here or here, if he goes here or here, there is a equal probability of getting into a pit. So this is pretty risky. So agent cannot make any decision here. So what the agent will do is agent will go back. Agent will go back to this A state. If you are a human, you will do this only, right? Now where the agent can go? Agent can go to the top. Agent can go to the top because agent knows that when the agent is in 1, 1, he is not sensing anything. So already he has explored the right side room. So now he can go to the top. So the agent will go here. When the agent goes here, what he will sense? When the agent goes here, Wumpus is here. So if you go back to the diagram, Wumpus is here. Okay. So we don't know where is Wumpus. Agent don't know where is Wumpus. But when the agent goes here, he will experience stench. He will experience stench. If he is experiencing stench, then what does it mean? Wumpus should be here, or Wumpus should be here, or Wumpus should be here. Now, out of this, what the agent knows? Agent knows that Wumpus is not in 1, 1 because he is coming from 1, 1. So this option is ruled out. And Wumpus is not here also. This also, if you see, that is 2, 2 also. Wumpus, there is no possibility of having Wumpus in 2, 2 because if Wumpus was here, then previously when agent was here, at that time the agent should have sensed stench also, but agent has not sensed stench. Agent has only sensed breeze, right? So which means that Wumpus is not here. Which means Wumpus is not here because previously when the agent was in 2, 1, right? Previously when the agent was in 2, 1, the agent sensed only breeze. It has not sensed stench. So from this, it is confirmed that Wumpus is not here. So now agent understands that Wumpus should be here only. Okay. So far it is fine. Now there is also another observation. What is that? Agent here at this place, at this point, agent is not experiencing breeze. Agent is experiencing only stench. If agent is only experiencing stench, and agent knows that Wumpus is here. Okay. So what does it mean? Agent is experiencing only stench. Agent is not experiencing breeze. As agent is not experiencing breeze, it means pit is not here. Because previously when agent was here, he experienced breeze. Okay. So which means pit should be either here or here, like that he thought previously, right? But now when agent is here, he is experiencing only stench, and already it is confirmed that Wumpus is here. So here there is no pit. If pit is here, then agent should be experiencing breeze, but agent is not experiencing breeze. So what the agent will do? So now the agent has confirmed that there is no pit here. So the agent can comfortably move here, right? When the agent moves here, what he will experience? So here, actually when the agent comes here, he will not experience anything because there is no pit in the adjacent square. There is no pit here, there is no pit here, there is no pit here, there is no pit here. Okay. Wumpus is also not here, Wumpus is also not here, Wumpus is also not here, Wumpus is also not here. Right? Okay, so now the agent is here, right? Which means the agent can go anywhere. The agent can go in all the four directions, but already the agent has explored 2 comma 1 and 1 comma 2. So the agent will not go to 1 comma 2 and 2 comma 1. So there are two places the agent can go. One is the agent can go to 3 comma 2. This is one possibility. Or the agent can go to sorry, this is what, this is 2 comma 3. The agent can go to either 2 comma 3 or the agent can go to 3 comma 2. So these are the two possibilities the agent can do, right? Okay, so let us assume that agent is going here. If the agent comes here, this is 3 comma 2. This is the worst case scenario. Okay, if the agent comes here, then what the agent will experience? If the agent comes here, there is a pit here, so the agent will experience breeze. Okay, agent will experience breeze. So so here the agent will experience breeze. Now what does it mean? If he is experiencing a breeze here, it means there is a pit here, or there is a pit here, or there is a pit here, right? Agent already knows that there is a pit here. That doesn't mean that agent already knows that there is a pit here because of his previous knowledge. Okay, that doesn't mean that he can rule out the chances of having a pit here or pit here. There may be a pit here, and also there may be a pit here, or at least in any one of the place there may be a pit. So agent cannot take any risk. Agent cannot take any risk. So the agent will come back. Agent will again come back. In this cell, again, agent is not sensing anything. Now all the three directions he has explored. So the only direction he has not explored is this cell. So that is nothing but 2 comma 3. So the agent will go here. Agent will go here, and here is the gold. So agent sends the glitter and he will grab the gold. Okay. So this is how, and what do you call, if a human is doing in this situation, this is how the human will perform. Okay, I mean, if the human is applying all the logics correctly, right? Or okay, so if the human is applying all the logic correctly, then this is what the human will do. Okay, here there is nothing, no assumptions. Here everything is, this is called as inference. This is here there is nothing went wrong. If all the calculations were correct, then whatever we are doing is correct. So that is called as logic. So this is called as logic. So why we discuss this example is to have you feel like what is logic, right? Like how we are building up from known facts, how we are building up the further facts. So whatever we have discussed, that's what shown here. Initially agent was here, so it means he can go here or here. He's coming here. Here he is experiencing breeze, that is represented as B. So a pit may be either here or a pit may be here, right? So the agent is coming back. So the agent is coming back, and the agent is going here to the top. When the agent comes here, he is experiencing stench. Okay, he is experiencing stench. So when the agent is experiencing stench, the agent knows that the umpus should be here only, because previously, if the umpus is here, then previously when the agent was here, it should have experienced stench, but it has not experienced stench, so it means umpus is here. And also at the same time, here the agent is experiencing only stench, no breeze, which means there is no pit here. If a pit is here, then here also the agent should experience breeze. Previously, when the agent was here he experienced breeze. So the agent can comfortably move here. Okay. Now after moving here, this is very safe position. There is no stench, or there is no stench, or there is no breeze, which means all the four adjacent cells are safe. Everything is safe. But this and this the agent has already explored. So only the other two are left out. But as per this diagram, it is assumed that agent is going here directly. Agent is not going to this path at all. Agent is directly going here and it is grabbing the gold. Okay. Even so, we have discussed that agent first went here. Even if it has went here, it will experience what? It will experience breeze. As it experiences breeze, it will doubt that there may be a pit, so it will come back and it will go up. Right. So anyway, it will grab the gold and it will go back. So this is the whole story. Fine. So this example we'll be using over a period of time. So that we have discussed that. Okay. So now, what is logic? We here in the previous example we use logical reasoning to find the gold. So logics are formal languages. So basically logics are one type of languages to represent information, and based on this information we can draw some conclusions. Right. And this logic includes syntax and semantics. Syntax represents the grammar of the language. So the language will have its own grammar or the rules, that is called a syntax. And semantics represents the meaning of the sentence, or it represents the truth value of the sentence. Right? For some sentence the truth value may be always true, and for some sentence the truth value may be always false. For some sentences the truth value may change with respect to time. For example, consider the language of arithmetic. So there are different types of sentence. Here we are taking the language of arithmetic. For example, this is a sentence: x plus 2 greater than or equal to y. This is a sentence. But this is not a sentence because there is no meaning in this. So the sentence should have a syntax and also semantics. It is following some syntactic structure, and also it has meaning. But it is not following any syntax. X2 means what? Is it x into 2 or x to the power 2 or what? So there is something is missing. X2 plus y greater than empty set. So this is not a correct way. So hence we say that this is not a syntax, because it is not grammatically, or it is not syntactically following any fixed grammar or rule, and also it is not making any sense. It is not making any meaningful. It is not understandable. Fine. Whereas x plus 2 greater than or equal to y, this is a sentence. Now in some world this sentence will be true, and in some world this sentence will be false. For example, this sentence is true in the world where x equal to 7 and y equal to 1. Okay. If x is 7 and y is 1, this sentence is true because it is 9 greater than or equal to 1 is true. Okay. If x is equal to 0 and y is equal to 6, then this sentence is false. So this sentence is false in the world where x is equal to 0 and y is equal to 6. If x is 0 and y is 6, then it becomes 2. Is 2 greater than or equal to 6? No, so it becomes false. Right? Okay, so this is just an example for sentence. Yeah, now we are going to discuss an important concept called entailment. So entailment means one thing follows from another. So the entailment is represented using this symbol. So this is the symbol which we use to represent entailment. So here we say that KB entails alpha. So this is how it should be read. KB entails alpha. It means that, so what do we mean by that? KB entails alpha. KB entails alpha means alpha is true in all worlds where KB is true. See, this is little tricky. Please understand properly. Alpha is true in all worlds where KB is true. What does it mean? It means that, say for example, alpha is a set which is given like this. Alpha contains some statements: statement 1, statement 2, statement 3, statement 4, statement 5, and statement 6. Okay. Let us assume all these statements are true. S1, S2, S3, S4, S5, S6 are true. Okay. Fine. Now KB, assume KB contains some sentences here: S2, S4, and S6. So now we can say that KB entails alpha. Okay, KB contains only these sentences: S2, S4, S6. and all these sentences are true in KB also. So then we can say that KB entails alpha. Is that clear? So entailment means a knowledge base KB entails a sentence alpha if and only if alpha is true in all worlds where KB is true. Right? See, this you should understand properly. Alpha is true. See this, alpha is true in all worlds where KB is true. For example, you take 1 by 1 alpha. Alpha is true. Actually, this, see, this thing you should this thing we should understand in a proper way. Alpha is true in all worlds where KB is true. So actually, you should understand this in the reverse way. Don't took it. Yeah, the meaning also, it's English meaning is also, if you sense it, if alpha is true, if alpha is true in all worlds where KB is true. So we have to start from where? We have to start from KB. You should not start with alpha. If you start with alpha, you will land in trouble. Okay. If alpha is true in all worlds where KB is true, so you have to start with KB. So start with KB. S2, KB is true. So S2 is true in KB. Is it true in alpha? Yes. S4 is true in KB. Is it true in alpha? Yes. S6 is true in KB. Is it true in alpha? Yes. So KB entails alpha. Is that clear? Okay. So wherever KB is true, there alpha is also true. Or simply understand that way. KB entails alpha means wherever KB is true, there alpha is also true. There alpha is also true. In that case, we can say that KB entails alpha. So in this case, if you take this example, it is KB entails alpha is true. Because you take anything in KB, S2 is true, that is true in alpha also. S4 is true, that is true in alpha also. S6 is true, that is true in alpha also. Right? Here KB entails alpha, but alpha does not entails KB. This is false. Alpha does not entails KB. Okay. If I say alpha entails KB, then what does it mean? Wherever alpha is true, there KB is also true. But if you take S1 is true in alpha, but S1 is not at all in KB. Okay. So in that case, it fails. So alpha does not entails KB, but KB entails alpha. So this is what the meaning of entailment. Fine. So, and now let us try to understand what is meant by models. So in the world of logics, the logicians use the term models, which are model represent a world. Model represent a world in which something is true. Right. So for example, we say that M is a model of a sentence. M is a model of a sentence alpha. If alpha is true in M, right? M is a model of a sentence alpha. If alpha is true in M, so M of alpha is a set of all models where alpha is true. When you say M of alpha, it is a set of all models where alpha is true. Okay. What is M? M is a model. M is a model of a sentence alpha. If alpha is true in M, when you say M of alpha, it means that alpha, M of alpha is a set of all models. It represents set of all models or set of all worlds where alpha is true. Okay. So models are nothing but world. Models are nothing but world. World is represented as models. Right. So when you say M of alpha, which means that alpha is true. Alpha is true in all models. M of alpha is true in the set of all models. Right. So here, right. So here, so this diagram you can see, this is M of alpha. So in this entire thing, alpha is true. Here also 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 alpha is true. Everywhere alpha is true. So that is what M of alpha represents. It's a set of all models where alpha is true. Right. But here we are saying that M of KB. M of KB is this. M of KB is a subset of M of alpha. M of KB is a subset of M of alpha. When you say M of KB, KB is true only here. only here. KB is not true here. Here KB is not true. It's not true. KB is true only here, right? So when you talk about entailment, previously we discussed that KB entails alpha. So KB entails alpha under which condition? With respect to models, if you speak, KB entails alpha if and only if M of KB is a subset of M of alpha, right? What is M of KB? The set of all models where KB is true. What is M of alpha? The set of all models where alpha is true, right? So KB entails alpha is true if and only if M of KB is a subset of M of alpha. Okay, fine. Okay, so now let us once again, so now let us understand this entailment with an example. So we are now going to study this entailment with an example. So this is a reduced Wumpus world problem. This is not the same. At the top level, it is the same, but we are considering a reduced Wumpus world problem where we consider only pits. We consider only pits. That is, we assume there is no Wumpus. There is no Wumpus. Okay, there is no Wumpus. We consider only pits, right? And consider this is the current state of the world. This is the current. So the Wumpus world contains 16 squares, but this is the current state of the world. Initially, the agent was here, and at that time, the agent has not sensed anything. No breeze. Okay, we are talking about only pit. So there is no question of stench. So the agent has not sensed any breeze. So the agent has moved here. Okay. When the agent has moved here, the agent has sensed breeze. The agent has sensed breeze. B, I'm saying. It means that we know that it means that pit is either here or pit is either here. Okay. This is the current situation. This is the current situation. But this thing, how we are going to now, so this is a limited world Wumpus world problem. Okay, now so agent has this knowledge. What knowledge agent is having? Agent knows that this cell is okay cell, and there is nothing he has experienced here, which means agent has not experienced anything here. It means no pit here, no pit here. So but agent came here. Here he has experienced breeze, which means pit is here or pit is here. These are the knowledge of the agent. But for the time being, forget the knowledge. For the time being, forget the knowledge. These two cells anyway it is explored. So leave this. These are the remaining possibilities. Okay, these are the remaining possibilities. Now we are considering a reduced world where a pit, where we are considering only pit. So what about the possibilities of these cells? Forget about the existing knowledge. So what are the possibilities of having a pit here? So what are the different combinations are available? One is all the three cells may have a pit. All these three cells, here also you may have a pit, here also you may have a pit, and here also you may have a pit, right? Another is any two cells you may have a pit. Okay, so I'll say what is the possibility of pit. So I'll say one is 1 1 1. All three are pit, or this two are pit and this is not a pit. Okay, or this two are pit and this is not a pit, or this two are, this is we have discussed. Okay, what are the other combination? This two are pit and this is not a pit. Okay, or there is only one pit, this one is the pit. Okay, or this one is a pit, or this one is a pit, or there is no pit at all. So there are how many possibilities are there? 1 2 3 4 5 6 7 8 possibilities are there. Okay, we are not using our knowledge. If you don't use the existing inferred knowledge, all those things also, what is the total possibilities? There are, we have these 8 combinations. We have these 8 combinations. Okay, so this 8 combinations is our knowledge base. This is our knowledge base. So this is our original basic knowledge base. Okay, right? So this I think it is understandable. Currently agent is here. These two are already explored, so we are not considering this. So this situation says that there is a pit here. And this situation says that there is a pit here. This says that there is a pit here. This says that there is a pit here and here. This says that there is a pit here and here. This says that there is a pit in all the three. This says that there is a pit here and here. And this says that there is no pit anywhere. So these are the possibilities. Okay. So this is the overall knowledge base. Now let us apply our knowledge. Now agent knows certain facts. Based on agent's fact, apply the knowledge. What agent knows? When agent is here, the agent has not sensed anything, which means there is no pit here. Which means there is no pit here, and there is no pit here. This is already we know. This is already it is mentioned. Nowhere here there is pit. So it means no pit here. So wherever there is a pit here, you can ignore. So this can be ignored. This can be ignored. This can be ignored, and this can be ignored. Okay. Is that fine? And one more thing, when the agent comes here, the agent is experiencing breeze. The agent is experiencing breeze. Okay. Which means that for sure, the agent knows that there is a pit either here or there is a pit here. Okay. When the agent is here, the agent is experiencing breeze, which means that surely there is a pit either here or here. Okay. So any one of these places should have a pit. So agent cannot assume that both these places are not having pit. Are you getting? When the agent is here, the agent is experiencing breeze. So agent knows that surely any one of these places is having a pit. So agent cannot assume that both these places were not having a pit. So this also is ruled out. Okay. So now our KB is reduced to this. So this is a reduced KB. This is the actual KB, but with this knowledge, with our knowledge, with the agent's knowledge, the KB is reduced this. Fine. So this is the reduced KB. So this is the reduced KB, right? So that is all possible Olympus world consistent with observation and the physics of the Olympus. Physics means whatever the knowledge we know. So that's it. So with that, this KB, our KB size is now reduced. Okay. Now let us assume some alpha. This is the alpha we are taking. What is that alpha? The statement. This is a statement. This alpha 1 is the statement. This alpha 1 is the statement. This statement says that 1, 2 is safe. 1, 2 is safe. Now go to our original diagram. See here. Here in which cells 1, 2 is safe? Which is 1, 2? First of all, let us identify. So this is 1, this is 2. So this is 1, 2. So where are the whichever the positions or whichever the states where 1, 2 is safe? So here 1, 2 is safe. Here 1, 2 is safe. I mean there is no pit in our drawings, right? Here 1, 2 is safe. Here 1, 2 is safe. Here 1, 2 is not safe. Here it's not safe. Here it's not safe. Here it's not safe, right? So this is the world where 1, 2 is safe. Possibility, right? So now that is what is alpha 1. So that is how we got this alpha 1. Are you getting? Okay. Now let us understand whether, now what about this statement? KB entails alpha 1. Is it true or false? Yes, it is true. Because wherever, what is KB entails alpha 1? It means wherever KB is true, alpha 1 should be true. Is KB is true here? What about alpha 1? Is it true? Yes. Is KB is true here? Yes. Alpha 1. So the, KB is true means this statement 1, 2 is safe. Is that is true here? Yes. Is alpha 1 is also true? For alpha 1 is also it is true? Yes. For here is KB, the statement is true. 1, 2 is safe. Yes. For alpha 1 is also it is true. Here is it true? KB, the statement 1, 2 is safe. Yes. For alpha 1 is also true. So this actually is an example for KB entails alpha 1. Right? Let us check one more example. So here let us assume the same KB. Our KB is same. There is no change in the KB. This is the KB. Now we are changing the alpha. Now our new alpha is alpha 2 is equal to 2 comma 2 is safe. What is 2 comma 2? Go to our original diagram. From here we will try to understand what is 2 comma 2. So from here you see 2 comma 2 is this position. This is 2 2. So in which states 2 comma 2 is safe? Here it's not safe, not safe. Here it is safe. Here it is safe, not safe, not safe. Here it is safe. Here it is safe. So this is the world where 2 comma 2 is safe. Okay. But what is KB? Let me draw here itself. What is our KB? Let me use a different color. What is our KB? KB is this. KB is this. Okay. Now this is KB. This is alpha 2. Now can you say that KB entails alpha 2? No, KB not entails alpha 2. Because wherever KB is true, alpha 2 is not true. What is alpha 2? Alpha 2 is a sentence which says that 2 comma 2 is safe. 2 comma 2 is safe. Okay. So here, so if you see here, this is KB. This belongs to KB. So here 2 comma 2 is safe for KB. But is it safe for alpha 1? Yes, it is safe. Here, here 2 comma 2 is not safe for KB. Okay. Here 2 comma 2 is not safe for KB. So the statement says that wherever KB is true, alpha 2 should be true. Right? But here it is not true. KB is false. So KB is false, and alpha 2 does not have alpha 2 does not have this information itself. Are you getting? And if you see this here, KB is false. This statement is false, and alpha 2 does not have this information at all. So here KB does not entails alpha 2. Okay. So that's what it says. 2 comma 2. Here we say it is safe, but actually it is not safe, and also this is not available in alpha 2. So here we cannot say that KB entails alpha 2. KB does not entails alpha 2. Okay.